What are those input? We can say that the input, for example, one is maybe her height. The second one is, we say, index number. The third one is maybe we say weight. And the fourth one, we said maybe body mass. The fifth one, we see maybe the hairstyle or the hair length. So we can go on and on and on. All these inputs that we have, they are variables that will help us to describe the type of output that we are looking for. And we say that that output is a biomedical engineering student. So we go back again and then we ask, have we exhausted the input? We said no. So we now go back again and add a couple more inputs that will help us to define that output called biomedical engineering student. So we apply all this input into this function. So when we take that biomedical engineering student, we will list out all those input parameters. The hair height, the hair length, we measure it in millimeters. So what is the hair length? Then the weight, we measure in kilos. What is the weight? The index number, maybe what is the index number? A certain number of digits. So we go on all these parameters. We provide that. And then those parameters will be passed through a function, and the function will give us our output called biomedical engineering. So that is what the fact that we are providing input with output pair that we are using through a function, it will give us, after we have used this set of functions, a number of the samples. So we take one biomedical student as this one biomedical student that we take, we call it a sample. And that sample, we are picking it from a number of samples. So we have 1,000 students. Each student will have its own set of all the parameters that we decide on. Each student will have its own set of parameters. And then when we pick each student, then we say this student, which department does it belong to? It belongs to a particular department. Then we are telling the model that function is learning that this particular student information that you have given to me, it is biomedical. So that is it. So the system is learning all that relationship that deals with that particular student and the biomedical assignment. If you pick another student, it will look at all the features. Each student that we pick, we go through that process and then we link it up. So the model learns, the function learns that relationship, and that function we call the algorithm. It learns that relationship until we are done with that, and it gives us another function called g of x. And that g of x now becomes what we call our model. That g of x becomes what we call our model. So now with the new function called g of x, which is our model, if we provide that, if we take any student, a sample of any sample or any student, and we provide this, the number of input or attributes for that particular student, it will give us our output. So if the algorithm has, which we call our function f, if it has learned that relationship very well enough, then when we provide that input s, it will give us that output that corresponds exactly to what we are looking for. So typically, we use the supervised learning machine learning model when we want to apply a function that is an unknown. So after we have gotten the model or that whatever G function, any function that is unknown, then we now apply it. And based on that, your model should be able to give you an output. So we can see the learning process as the data samples that we have. If we have 1,000 students, or let's say the students who have signed up to this program, we have 70 of them. And we now want to organize them by departments. We want to organize them by departments. So we take each student and then we agree on which attributes we are going to use to define them by their departments. So the number of students we have, we refer to them as what we call our training data set. Our training data set. And each training data set, I have the input variable X. The one here denotes the student. So if I have 5 students, S will be student number 1, S2, student number 2, all the way up to student number N. And each student number, I'll have to define the same variables that I'm using or attributes. And then I will tell the function that somebody is making noise. Please mute yourself. That student will indicate the class of that student, the department of that student. So this set of data that we are going to use for the model to learn from, we refer to that as the training data set. So the set of data that we are going to use for the algorithm to learn from, that becomes our training data set. So this set, the algorithm will be familiar with these sets because it's learning the relationship from this data set that we have given it to it. Then we have another data set, which we call test data set. After the relationship has been learned between the input and output from that sample that we give to the algorithm, then the algorithm will give us our model, which we call our G. That is our model. Now, we now have to have another test, a data set that we want to use to validate whether the model, the algorithm has learned enough so that it will be able to give us a prediction of who we are looking for. So, as we said the last time, the data set that we have, we normally split the data set into 2 types. The type that we are using to learn the relationship, and the type that we are using to test whether the relationship has been learned enough. So the test data set is again each student. So out of the 70 students, we can decide that we are using 60 of them to learn the relationship. And the 10 of them, the function or the algorithm has never seen that. It hasn't seen the 10. So we'll now pick each of the 10 students, one of them, their attributes that I've called asterisk, then I'll pass it through it. And then it will give me a prediction. Then I can match the prediction with what I'm expecting to see whether it is correct or not. If it is not correct, then my model has not. So I will test all the 10. And all the 10, I will see how many of them my model has tested correctly. Okay. So where do we use these supervised learning techniques? We find the supervised learning techniques application in different types of problems, engineering or scientific or whatever problems, different types of problems. Now, some of the problems that we can use supervised learning techniques that they can work very well. Supervised learning technique, areas that they can, problems, nature of problems that they can learn very well. Please, those who are talking, can you mute yourself? When we have something called binary classification, classification here means that you are dividing your output into, binary means 2 states. When we talk about binary, At least we are all familiar with binary digits. Binary digits either 0 or 1. In other types, we can say either black or white, either yes or no. So when we have problems that we want to classify them as either a yes or no case, then supervised learning binary classification is one of the best approaches to use to do that. When you want to divide into two categories, we want to classify students as male by gender, male or female, just two distinct classes. So we have what we call binary class classification. And the classification is putting into categories. That's what it means. A binary means two classes. Then we also have another type of application where we call multi-class classification. Multi-class classification. So if we are not classifying students who have registered for this course into gender, that is male or female, then we have another way we can classify students. We can classify them by departments. So the question we ask ourselves, how many departments do we have? We have 5 departments. In that case, we have 5 possible outputs that we need to classify students into. So multi-class classification. So where we need to have a situation where we want to solve a problem which can put into a number more than 2 classes or categories, then supervised learning for multi-class classification will be the best suited process for handling that. Now, beyond the to classify into 1-2 classes or multi-classes, now over here it's not telling us values. It's only giving us this student belongs to this department. But it's not telling us the actual GPA of the student. The GPA is a numeric value. It's not telling us. It's only telling us this student belongs to biomedical or computer or agri or food or material. This student is a male or female. Now, all this we can even decide to use if we want to classify students by regions or by ethnic background or whatever we choose. Once it is more than that, we can do that. Now, the moment we want to now have something that gives us actual numeric values, then classification will not help us again. In that case, we go for a supervised learning model called regression. So regression, and the regression, it will help us to predict the actual value of what we are looking for. So we can use regression, supervised model regression to do that. Then the last of the supervised learning model is one technique called ensembling modeling. Ensembling modeling. Now, what do we mean by ensembling modeling? Now, the ensembling, we can have, when we put a number of supervised learning together, we combine the decisions of multiple supervised, maybe 2 or more supervised learning model. We can combine them to help us decide, make a decision or something. So when we put those things together, we call them, when we put a number of supervised learning algorithms together, we form what you call ensemble learning. And the ensemble learning, if we have a situation where maybe a type, 2 types or 3 different types of machine supervised learning model, each of them will have their own strengths and weaknesses. So we think that we want to get a good result, but if one is good in one area, another is good in another area, and want to combine their various powers so that we can get the best of results, then we can use ensemble learning. Now, the caveat there is, if we are using, let's say, supervised learning algorithm 1, supervised learning algorithm 2, supervised learning algorithm 3, and each algorithm is giving us very good performance, then there is no need to combine them, because once each of them is giving you very good performance, then you can choose just one of them. But if one is good and one is not too good, but they have very good performances, I mean, in terms of abilities, then we can combine them to form what we call ensemble learning. So what are some of these standard supervised learning algorithms that we can use to develop models for application? One of them is what we call naive Bayes. Naive Bayes algorithm. The second one is what we call k-nearest neighbor algorithm. K-nearest neighbor algorithm. The third one is decision tree. The fourth one is random forest. The fourth one is random forest. The fifth one is support. I've alternated because random forest is a form of ensemble learning. Random forest combines a number of decision trees to form an ensemble. That's why I decided to alter them out, right? Just shift their position. So we also have another algorithm called support vector machine. And the last algorithm, but not the least, is what we call linear regression. So this linear regression performs what we call regression model. We use it for regression modeling. So each of these algorithms we have put in here, according to the outline that we've given to you, as I said, I didn't do this in the previous training programs, but this year I've introduced them. So each of these algorithms, we will develop each one of them so that you can see how they perform. Okay, now we come to unsupervised learning. As we said earlier, unsupervised learning, they operate without any external guidance. So what they have to do is the algorithm has to discover its own ways of organizing the data into what we call groupings. And the groupings are done in accordance with some modality. So it organizes the data because it doesn't have any external agent or guidance to tell you that, okay, this data that I've given to you, it belongs to biomedical. This data I've given to you, or these features or input attributes I've given to you, it belongs to agric engineering. No. So there is nothing like any guidance. So the algorithm has to figure itself out how it can be able to organize these sets of information into what we call groupings. And therefore, there must be a modality. And the modality is that it looks out for what we call degree of similarity. So it organizes them based on how similar each elements are, and you put all elements that are similar to each other into one group, and that group it calls a cluster. So in that case, it has to go through and discover its own self. So sometimes we refer to the unsupervised learning as what we call knowledge discovery learning. They have to discover themselves. Now, there are two types of unsupervised learning problem. One is what we call clustering, and the other one is we call association. So we talk about clustering, it has to, given the data, it organizes them into clusters. And each cluster, when we have an input, it tries to associate the data that we have into what we call the cluster that we create. So again, we will go through each of these type of unsupervised learning. Now, when we come to unsupervised learning techniques, they are very good in handling problems that involve what we call clustering, splitting of data into subgroups based on their level of similarities. And then also, we also use unsupervised learning to do what you call, when we have problems for anomaly. So, for example, one of the things that the human being, when we come to very soon, we'll be starting with that biological aspect of the learning process. But when we come to natural human tendencies, ability to detect things, they are not based on what we call, some of them, yes, they are based on what we are familiar with, but most of the time, they operate on unsupervised learning principle. So when we have to detect any form of unusual occurrences, occurring in any information, then we have what we call anomaly. Then we have, again, association, as I mentioned. And then the last one is what we call dimension reduction. So unsupervised learning also, when we are dealing with, please, can you minimize yourself, please? When we are dealing with reducing data, then one of the useful techniques that we can use is unsupervised learning. Now, what do we mean by data reduction? As I said earlier on, we use the student again, the attributes of the student. I think last week I mentioned it. For example, the hair, length of the hair is the length of, can we say that the length of the hair of the student will adequately help us in establishing the department of that student? Even though we have seen it as an attribute, we have listed it. If it's not going to help us effectively, that means that that data, we can take it out without necessarily having any impact on the performance of our detection process. So such attributes or input information that would pass, we can take all of them out. When we take all of them out, if we have an attribute size of 10, and we reduce them to about, let's say, 3 or 4, then it reduces our computational time. Please, can you minimize yourself? Then it will reduce our computational time. So these are areas that when we have to develop an application to solve a problem of a particular nature that conforms to this, then the best technique to use is unsupervised learning. It doesn't mean that we cannot use supervised. We can use supervised, but if we have a label, if we have a desired target, then we can use supervised. But if we don't have any desired target, where the solution, we have to navigate to identify patterns and trends in it to be able to do that job, then the best technique to use is unsupervised learning. Now, some of the key unsupervised learning algorithms that are used, one of them is what we call the K-means algorithm. We use it for unsupervised learning. Then we also have what we call principal component analysis. we use this one to do feature reduction. This one helps us with clustering. This one helps us to deal with dimension reduction. Dimension reduction. And then self-organizing map neural network also help us to do clustering. Then there is another one, isolation forest. It also helps us to do isolation forest helps us to do clustering. So these are some of the popular ones. Isolation forest is one of the new ones that people are using nowadays more to do. So we can combine a number of them to achieve the same solution that we are looking for. Now, we come to the third one. Hello, Derek. We come to the third one, which we call reinforcement. Reinforcement learning. So the reinforcement learning, again, that one also has, as I said, it uses a reward and a penalty system. So this type of learning, we have what we call some limited guidance, so that the guidance aid in determining whether the solution we have is achieving the desired target. And so it is sandwiched between the supervised learning and the unsupervised learning. Now, with this type of learning, the algorithm is only provided with a grade or a score. That's a guidance. And that score is used to determine whether a particular solution is approaching what is expected or is deviating from the expected. So once it is approaching what is expected, then it says that you are doing very well. I give you credit for that. And then if it is not, then it gives you something that, no, I give you penalty. It means that you are not learning as expected. So that is a summary of the reinforcement. So let me quickly move on to the last segment on the application of the reinforcement. The reinforcement, we see application, a solution that deal with robotics. Reinforcement is applied there. Solutions that deal with games, video gaming, reinforcement is applied there. And a solution that deals with resource management, that solution is also applied there. I've given myself 30 minutes, so let me wrap up on this. Semi is just the next one. So let me wrap up on the last one. Let me skip the symbol. We'll talk about each of them details. So the summary for now, the various tasks, we can see that the tasks can be into two main types, either clustering algorithm, classification algorithm, regression algorithm, or clustering algorithm. These are the three main tasks that we find ourselves in developing machine learning models to meet that solution. So either we are dealing with clustering algorithm, either we are dealing with what we call regression, classification problems or tasks, regression problems or tasks, or clustering problems or tasks. So these are the key tasks that we see most machine learning solutions conforming to. So we'll now move on now to the next segment that deals with now the artificial neural network, how the human brain learns, how the human brain learns processes. And then we'll do some small, that's like we did with the last week. We'll do some small play around certain things. Okay. So now let me move on to that segment. Okay. So now we now introduce ourselves to what we call artificial neural network and how the human brain learns. Now, the first fundamental unit that we have, this one biomedical students can relate more to this. The fundamental thing that we have is what we call a neuron. So this diagram that I have here with the yellow, blue, red, these are, each cell is a neuron. And all the neurons come together to form the brain. And for us, each neuron is from biology, is a biological cell. But for us, in terms of machine learning, it is a processing unit. A processing unit. Each neuron will do just one process operation. It's a processing unit. So we refer to the biological neuron in machine learning as artificial neuron. We refer to the biological neuron, whether in the human brain, in the machine learning language or parlance, as artificial neuron. Now, so when we have a number of the biological neurons that are being put together, connected together in a particular hierarchy, to achieve a particular objective, then we refer to that as neural network. So biological neurons that are being connected together in a particular hierarchy, like what you are seeing here now, we have the yellow connected to a blue, another yellow connected to a blue, and then the blue connected to a red, then the second blue connected to a red. See that we have a hierarchy. They are moving from one direction to another direction. So in the context of what I have here, we say that they are moving in the forward direction to give us an output. So you see that we have the two reds here. Two reds here. Now, these two red segments here, a while ago, we talked about what we call supervised learning. And we talk about classification. So if we are to create a machine learning model to classify students by department, we have 5 departments. In that case, we are going to have 5 red cells here. Each cell will be denoted to each department, so that if we put in different colored cells, then we can say that, okay, this cell belongs to this department, this cell belongs to this. But so each is a neuron, and they are connected. The red that we see here, we call it our output level or output layer. And then our input, we provide it here. And then the other, in between the input and output, there are different types of neurons, but they are connected in a particular hierarchy. So when we have the biological neurons that are connected, if we have biological neurons that are connected in a particular architecture, then we say that is neural network. Now, if in the machine learning language, if it is artificial neurons, then we refer to that as artificial neural network. Then we refer to that as artificial neural network. So most of our machine learning language that we use for either deep and shallow models, so we'll go through each of them. We use neural network architecture to do many of the things that we'll be seeing that we'll be doing. Now, each of the neurons, we say that they perform a simple processing element. So that element they can do what you call a nonlinear operation. Okay, so let me just put it at this point. They will perform a nonlinear operation, or they can perform a linear operation based on what we want it to do, the output we are expecting. And the artificial neural network architecture, it's a layered architecture. It can have a single layer structure or multiple layer structure. And the neurons are connected in the feed-forward direction or the feedback direction, or a combination of feed-forward and feedback. So we see a combination of feed-forward and feedback in different applications. For example, when we come to natural language processing, we'll see such architectures in there. When we come to time series analysis, we'll see some such applications in there. And then when we have the feed-forward direction, when we come to convolutional network, so we see all being applied in different levels of use. Now we look at some of the important properties of neural network that makes it such valuable tool for us to use in machine learning. One, they consist of simple elements, simple processing element. And the processing element is a neuron. Simple processing element, which is the neuron. And that's number one. They perform just simple, not complicated, very simple. We'll see that in the next few minutes, 5 minutes, you see what it does. Very simple process. But the biology people tells us that we have about 10 to the power 11 neurons, and they are all connected. So we see that the machine learning, the neural networks, they have very massive connectivity, and they are also parallel in operation. Very massive, and they are parallel. Now, the information about whatever we want to learn, they are stored in the connection. So when we take this connection, the link between the yellow and the blue, the connection, that is where the information is stored in. And biomedical people or the biologists, they will tell us something called the synaptic weight or synaptic connection. So that is where the information is stored. So it doesn't have any memory anywhere. It doesn't have any memory anywhere. The information is stored just in that link. And again, one of the unique properties it has is that the neurons have ability to perform nonlinear behavior. As I said, so the function that it performs, that is what dictates whether it is linear or nonlinear, by what we call an activation. So we'll see that again in a minute. They have ability to learn from examples in real time and generalize. Examples here means that we are talking about the data, the training data set. They have the ability to learn from that in real time, and they can generalize their output so that when you provide an input, it can generally give you an output. Now they have ability to adapt to changes in the environment. So when the environment changes, you provide new things, they can easily adjust. And you can see that, we'll see that again in a minute, how they do the adjustment. They are highly robust, very reliable, and one key thing is they are fault tolerant, and they can also withstand disturbances or noise. Final but not the least, the knowledge is represented in the same structure. So the network architecture that we have is that knowledge is represented in that structure. And then individual dynamics differ from collective behavior. So every neuron behavior is different. As long as they are on the same line, they behave differently. Okay. So this is the neuron. Then now we are looking at now how the cell, the unit cell, how it behaves. In terms of machine learning, that neuron We said it performs a simple process. Now, the neuron has from the biomedical, again, we say that we have what you call the nervous system. And we have what you call, again, external stimuli. So when you touch your hand to your skin, something has to sense to tell you that, okay, something is touching me, or somebody has touched me. What it then means is that there are what you call receptacles or nerves, receptacles, and they receive the information called a touch. So that receiver, see that what I have here, I have input S1, S2, S3. So this input S1, S2, S3, on and on. These are what we call the receptacles that will receive the input information. So the neuron will have input that will come to that neuron, and it will perform two basic operations. One operation is it will perform a summation operation. And then the second operation is it will perform what we call a transformation function to give us an output. So let me stop and give you a diagrammatic view of how it looks like. So let me use my whiteboard. Okay, so from what we were describing now, pen. Okay, that's what I was looking for. Okay, so this is the neuron, a unit cell. It performs two functions. One summation and then one transformation of the summation to give an output. Every neuron will give just only one output. It doesn't give more than one output, just one output. But the neuron will receive a number of input that will come. Each neuron will receive a number of input that will come to it. So in the case of the biomedical condition that we're describing, this is the hair information called 1. And then the second one is the weight called 2. Now the third one is 3, called the index number. And the fourth one is called let's say, called the height. We have defined this variable. Now, this is the input we are passing to a neuron, a biological neuron. But for us, this is the engineering model of the biological neuron. And so it's going to perform summation. Now, each input is connected to the neuron by a synapse. The biology people will say synapse or synaptic connection. But for us, the synaptic connection is a weight or a strength. So this one will go to this one. This one is also connected to this. This is connected to this. So this is connection 2, connection 3, and then connection 4. Now, so the first function of the neuron, it will perform a summation. So let me call this one 1. The summation will be S1 times W1 plus S2 times W2 plus S3 times W3 plus S4 W4. We have it finished. Now, every neuron has something called a bias. Every neuron is biased. So at least every one of you has done basic electronics. You see that we have something we bias something. So every neuron has a bias. So this bias has also another weight called B, and then it has an input S0. So what is going on there? So we now add that bias, that is S0 times B. So this is the first function that the biological neuron will perform. The human brain, each cell, this is the first function that it performs. After performing that function, then the next function that it will have to perform is what we call a transformation to give us an output. So our output, if our output from the neuron is Y, the output will be a function here, and that function is what it goes into this. This will go into this to give us our output. This function here is what we refer to as activation function. Activation function. That is a function that the biological neuron will have to perform to transform the function, the summation function that it has done to give us our output. So every single neuron will perform the same operation. Every single neuron will perform just to give us one output. Every single neuron will give us one output. So the question now has to do with what type of function are we going to use? It depends on what type of output we want to see coming from the neuron. So now, I go out of my board and then get back to my lecture, my slide information. So we see that this is a function. So now every neuron will perform this single operation here. That is why I said it's a very simple processing, just very simple operation. So now this is the operation. So now we now have to look at what type of function, which I call the function, this activation function, what type of function we want to perform. What type of function we want to perform. So that is what we now have to deal with. Now, let me pause here and make some quick statement here. Now, the TensorFlow and all those models we are going to perform, unfortunately, they are not going to give us a graphical view of how the neuron will look like. All we see is functions. So normally what I'm going to introduce you to, at least I will share some few things with you, and we'll see some small demonstration of this, where we can see the actual neuron, the depiction of the graphical view and everything in MATLAB. So far, currently, the scikit-learn, the TensorFlow, all of them, they don't provide the graphical view of this. So I will take you through a graphical view of this using MATLAB so that you can see how it looks like. MATLAB tool has gotten that graphical view for us. So we'll go through briefly and then we'll see how it works out. Recording in progress. Now, so we now look at the type of network. As we mentioned, the artificial neural network, we can have one layer structure. So we can have only one single layer here. And that single layer, we refer to that as a single layer network. We will see where we can apply them. We'll see a single layer network. It will have an input, each neuron will give an output, but just one layer. And that one layer will have a number of neurons depending on the design we want. If we want to classify department, we're going to have 5 neurons here. If we want to classify gender, we can have only 2 neurons. Right. Now, so we can have what we call a single layer network, neural network architecture. And then we can also have what we call a multi-layer network architecture. Multi-layer network architecture. So multi-layer network, we can have an input layer that will receive the inputs, an output layer that will give us output from the neuron, and then we can have a number of layers in between the input and the output. And those number of layers, we refer to them as hidden layers. Those hidden layers, we don't see them. We can see the input layer, we can see the output that is coming out, but we can't see the hidden layers. So if we want to design a multi-layer network, then some of the things we have to decide on is how many layers are we going to use for that machine learning model we want to design. If we want to use neural network development, then we have to figure out how many layers we want to have. Okay. So this is a very simple case, just one neuron. It is receiving a number of inputs, P1 up to P, based on the number of input that we have. This neuron will perform summation. Each input has a link to the neuron. So each input is connected to the neuron. When it comes to computer engineering, then we can say we have a number of inputs that we have wires, and the input is connected to a particular unit through wires. So we can see these as the W's as wires, that they are receiving different inputs. Okay, so we have seen this information already, where we perform this function. I should bring this one here first. Okay, this function comes in here first, and then the output of the neuron passes through the activation function, or is transformed to the output through a function. So now the question that is, this is a case of a single neuron with multiple input. Then we can have multiple neurons, one layer, multiple input. So we can see how the computation is going to go. This is connected to the summation. And remember I mentioned that all the inputs are broadcast to all the neurons that are in front of it. So this is how we see it. All the neurons will be connected to all the neurons will be connected to all the so we have an input here, input S1, S2, S3, S4, S5. So let me call this one, this is S1. That is a weight, S2. This is the hair length, S3. This is something that the weight, S4. Something is S5. Now, if it's a single layer, then this is a layer. Let's assume it has 3 neurons. Now, all the inputs here will be seen by every neuron. Every input here. So this S1 here will be seen by this neuron. It will be seen by this neuron. it will be seen by this neuron. That's why we see that they are fault tolerant. If this one is broken, at least all the rest will see. Then we come to this one. This one input will be seen by this, it will be seen by this, it will be seen by this. This will be seen by this, will be seen by this, will be seen by this. Again, this will be seen by this, will be seen by this, will be seen by this. And then finally, this will be seen by this, this will be seen by this, this will be seen by this. So every input that is connected to a neuron, it has a connection. So there is a connection there. And each connection will have some, what you call, strength. So this is how, so now this neuron here is going to perform two things. It will perform summation and it will perform a transformation function. This is where so this neuron here, let's call this one W1. Let's call this one V1. Let's call this one U1. Let's call this one K1, on and on. So now, this neuron here, it will perform first. The input that is coming here is X1. So S1 times the connection that is associated with it, plus this one is X2 plus its connection, which is, we said U1. Now plus S3, that's its connection. We call it V1. Plus S4, its connection, we call it K1. And then plus S5, its connection, we call it maybe P1. So this is just what the summation. Now each of these neurons will be biased. So this will be biased by B1. This will be biased by B2. This will be biased by B3. So now this is going to be plus the bias here, B1. So that is only for this first neuron. Let me call this one Z1. So now, if I'm looking for the output Y1 here, Y1 will be equal to the function which I haven't defined yet. And then that will give me my output for this neuron based on the input that is coming to it. That is what this neuron will perform. So when we are going to code, this is what the functions we are going to implement in the machine learning, if we are using neural network, this is how
Hello. I think Dr. Mills' line dropped. I don't know why. I would find out from his office.
Okay, thank you.
I just got in touch with Dr. Mills and he has a little bit um, connectivity issue, but then I think he's resolving it. So maybe in the next couple of minutes, he will join us. So whilst we wait for him, let me try and engage participants a little. Okay. So Dr. Mills was definitely speaking about the artificial neuron and how that neuron has been inspired by the biological neuron. And we have these neurons as the processing elements. These elements perform that summation operation, and also after that summation is done, it passes through the activation function. The summation operation, like we saw Dr. Mills demonstrate, was basically all right. The summation operation was basically a function where we have our weights. Better still, our synaptic weights multiplying our inputs. Now, one of the interesting things later on you come to appreciate is whenever we are dealing with multiplication, we need to be very careful because, especially with matrices, we have what I would say the normal multiplication and also dot products kind of multiplication. And what that basically means is normally the weights and the inputs are going to be, for instance, the input is going to be the data that's going to come, and the data can be in all manner of shape and form. The data will probably can be, let's say, like um, a column matrix or a row matrix, depending on how the shape of the data is. It can also be in the form of, for instance, let's say maybe a 2x2 matrix, and it could even be more. Now, if this data comes in here as the inputs, and we are multiplying by the weight, once it is a matrix, then we should be mindful about the dimensionality, because we cannot just multiply any matrix of any dimension with any matrix of any other dimension. So as we start with the coding process and trying to develop our own neural network, we are definitely going to encounter some of these problems. And there are ways we go about it. One of the ways is we can do a reshaping of the matrix. Okay, we can do a reshaping of the matrix so that it conforms to some of the weights we are getting, so that we have everything able to do that calculation. Now, once this is done, remember it is going to be a summation. Okay, so let me have my sigma over here, starting from, let's say, 1 and ending at n. And these are also going to be as a result of the number of inputs that we have. So if we have 4 inputs, then we expect to have an architecture where we have, these are input layer 1, 2, 3, 4, and then like Dr. Mills was trying to illustrate, these inputs are going to accept, or these neurons, these input neurons are going to accept the input data. So let's say it was a data where we have, let's represent this as X1. So X1 is, let's say, age. So X1 is age. Then X2 is, let's say, height. So let me represent it by h. Then X3 is X2. Then X3 is, let's say, weight. So let me do a W over here. Then X4 is, let's say, we have height, we have weight, let's say we have complexion, something like this. Okay. And let's say our objective for this kind of work is to build a network that's going to take these inputs, do the computation that the neuron would typically do, and then give us an output. So normally, most of the time, our inputs are kind of predetermined, and they are predetermined because of the number of features that we have. So the number of features is always going to determine our input layer. Then sometimes, or most of the time, our output layer is also predetermined. And that's simply because our output layer is going to kind of forecast us into the number of classes that we are going to have if indeed we are talking about classification. So that we may also have the output over here. And like I said, in this case, we are looking at male and female. Now, remember, these input features that we have will be, remember, at the end of the day, it is more or less a multiplication procedure that's going to happen. And that multiplication procedure means it should be some data that we can multiply. We cannot multiply A times C. Okay. So if it is A, B, C, there's a way we are going to convert that A, B, C into some categorical data. So in there, if you have gone through the outline very well, you see some data encoding and other things that we're working on. Okay, so I think Dr. Mills is here, so I'll pass on the baton for him to complete.
Thank you very much, Ken. My network just went off. I don't know. Yeah, so at least we are done with, at least that's an idea of how this thing works. So in terms of what I was sharing with you, this is just the multiple, what we call the multiple, the single layer, but multiple input. So what I was trying to do, this is an equation for each neuron will perform this. So this number of neurons that you have, this is each summation plus transformation function is one neuron's operation. So if you have 100 neurons on this line, each of them will perform. So you can imagine we have about 50 or 10 inputs and 100 neurons on this line. You can see how messy the net connection will be. And then each of them will be computing this to give along. That is why feature reduction of really features that are not relevant, removing them are concerned, so that at least it will reduce the computational time that you need for each one of them. If we have 10 inputs and we should reduce it to, let's say, 4, it means that the number of operations that we are going to have will be the summation will be much less. And that is why when we have features, when we come to the next, when we come to the other, as we are following, when we come to the data processing and all those things, we'll look at the feature aspect as well. So that is about that for the single layer operation. Then we come to the multi-layer. Now, the multi-layer, we may have an input layer, a number of a hidden layer that we don't see, and an output layer. Now, so the input and the output, we have control over. We see them. So, for example, the input, based on your number of input you are getting, you have a neurons for that. That will receive the input. So, assuming we are dealing with 6 input, we know beforehand that we are dealing with 6 input. So, your input layer, the number of neurons for your input will be 6. Your output, you know how many, if you are dealing with classification, you know how many output classes you want to have. So that one is under your control. But between the input and the output, you don't know. So this is where the design then comes in as to how many should I have, and each of the layers, how many neurons should I have at all in them. So that is what the operation is about. Now, depending on the number of how many layers we have in the neural network architecture, that gives us what we call the shallow network and then a deep network. When we have 3 layers, when we have this X is the input. When we have layer S1 and S2 and then Y, oh no, these are even 2 layers. So when we have 2 layers, input layer and output layer, plus 1 hidden layer, that is what we refer to as a shallow neural network design. So when you have only 1 hidden layer, then that gives you a shallow neural network. Now, when you have more than 1 hidden layer, then that gives us what we call a deep network. So you can design a neural network for a particular application where you can have maybe 4 hidden layers. It means that the learning will be much deeper than the simple 1 layer, hidden layer operation. So that is about that for that operation. They also go through the same concept. So now let's deal with the activation function. Then we are done. Then we'll now start with some dummy demonstration. So the activation function, we saw that we have computed this. So this is a summation, the first summation operation. And then this is the bias for the neuron. Now, depending on the type of output we want for the neuron, there are different types. And each of the types will tell us the type of function that we need to transform the summation operation. The first one is what we call the threshold limit. The threshold limit, it will give, regardless of whatever value this one is, it can provide an output of 1 or 0. Let me repeat. Regardless of whatever this size is, the moment Z is greater than or equal to 0, then the output will be 1. The moment Z is less than 0, then the output will be either 0 or -1, depending on what type of function we are looking for. So now, this type of function, what it means is that if we want to perform, so maybe let me float the question. Who can tell me what type of application will require us to do this, to use this? Who can tell me what type of application? That the output of the neuron will be either 1 or -1, or 1 or 0. Who can tell me? Please, you can speak out.
Classification.
Sorry?
Classification task.
Okay, so classification, but what type of classification?
Binary classification.
So exactly. So binary, when you want to do something that will deal with gender, yes or no, male or female, black or white, that kind of, then we can use this so that it will give us an output either 1 or 0. Now, the -1 here means that we are dealing with a function that is like this. Just 1 minute, let me share. Let me go to my app. My goodness. Hey. Oh. Yeah, okay. So that function, we said a function f of z. This is how we say it. It's equal to 1 for z is greater than or equal to 0. Otherwise, 0 for z less than 0. So we can plot this as this. This is z. This is y. So now it is 1. So this is 1. So either it is 1, and then when z value is negative, that means it is this, -1. So this is where we see it. It is either +1 or -1. So we can say that all those that are +1 here, we call it yes or male. And all those that are -1 here, we call them female or black. So this slide helps us to clearly separate out the gender issue or the black issue, black and white. So this is what we call the unit threshold function. Now, in the event that we don't want to see a negative value, a negative z, then in that case, we can say that z should that this should not be, if we don't want to see a negative this, then what we are saying is that we want it to be this. We want it to be this, and then what? 0 here. This is what we want. So it means that it's on the 0 line here. In that case, then we can use 1 or 0. Otherwise, 1 or -1. They give us, if we want to see negative element, in that case, then we use -1. If not, we want it to be 0, then to be this and 0. So this is what we call the unit threshold function, where we want to perform what we call a binary classification problem or classification problem generally. Now, another function that we can use, if it is not this, we can also use another function called where is my plus sign? We can use another function also called linear. F of z can be a linear function. Oh, it's 6 o'clock. Let me finish and then just quickly move on to that. It can be a linear function. A linear function means that you are dealing y is equal to ms, where m is equal to 1. So this is going to be z for z greater than or equal to 0, and then 0 otherwise. So what it means is that if z is positive, linear means it's going to be this. And then if it is 0, then we can do this. And this is what one of the activation functions that we use called ReLU, rectified linear unit. And it picks its name from diode, the way diode works. Diode will conduct in forward direction, negative direction is 0. So that's, but this one, in the case of forward, is linear. And then the output, that if it's Z is negative, then becomes a 0 function. So that is also what we call the ReLU function. So then the third function that we also use, which you may hear about it, is what we call a sigmoid, logistic sigmoid function. And that function, the Z is a nonlinear function. We define that function as 1 over 1 plus e raised to the power minus Z. So this becomes a nonlinear function. That is why we say that the neuron can perform nonlinear operation, because if it's performing nonlinear operation, its output will be this. So again, now when we put the value of Z, if it is positive or negative, we put it there, then we can see where the plot will be. So these are some of the functions that we use. And the last one is softmax. So there are different functions that are used in performing the transformation of the function. So at this point now, it is now 6 o'clock. We have about 30 minutes to end. I will now move on to a demonstration. We will continue on Friday on that. So let me see what I have here. So these are the functions. We'll continue on Friday on that. The learning. Now, yeah, okay. This is the learn. Okay, let me just skip and just do a demo. Then we'll continue on Friday. Now, I'm going to use a tool called MATLAB. I know that first year students, at least every student up to third year, they have done a course called Engineering Computational Tools. So we are not going to use it for the training program. We are going to use TensorFlow. We are going to use Python. But because they all don't have a graphical demonstration of the neural network architecture and the various type of architectures, that is why I'm using this to just give you a pictorial view of how it looks like, so that then from there, we can now go ahead and see what it is. So I'm going to call my MATLAB tool now and then do a demo for you on that. And then Friday, when we meet physically, then we'll continue with more of the demonstration. You see the MATLAB has opened now. So let me now share with you the MATLAB. Okay, so I'm going to use the MATLAB tool now to do something. Let me see. NN2. Okay. Okay, let me just check that. Let me do something again. Let me do manual computation. Okay, so I have the data that I want to learn using MATLAB. So I'm now going to do that for you to see. I have the data called, I have something called, I've created a data I want to test. So I've created a data set. And that data set, this deals with, let's say, student results and something. I just wanted to do something. So I have a number of input, 1, 2. So I have X1, S2, S1, S2, S1, S2, S1, S2. How many are there? I can count them. So let's say I have 10 students. So let me see. 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. Okay, 12 or 13. So these are the set that I have. And the 10 students, I want to classify them. I want to classify them maybe into departments, maybe one, either by gender, male or female. And each student, I'm using, let's say, the body weight, and then maybe any other feature. So 2 of them. So this one can be X1 for the student, and then X2 for the student. That's for the student 1. S2 for student 1, for student 2, S2 for student 2, S3 for student 3, S3 for, there are 2 of them, sorry, so we can put them that way. Now, each student that I have to now indicate the target that I want for each student. So I now provide my target. So I now provide a target for each student. I provide the target that I need. So I provide my target here. Oops. Okay, let me do a test so that I can see. 1 minute. Let me do a test script. I wanted to do this on the command line. Okay, just please give me 1 minute. Okay, 1 minute to see this. One minute to do this. So let me now come back here. Okay. So now, my target, I said the first one, I 0. So I'm doing 0 or 1. The next one, I said 1. The next one, 1. The next one, 1. The next one, 0. The next one, 1. The next one, 0. So how many do I have? 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11. So 11. So 1, 2, 3, 4, 5, 6, 7, 1, 1, 0, 0, 1. So now I've gotten my P is my data. That is the input data, and then T is a target. So now that I've gotten my input and the target, now I need to create something. So what I now need to do is I'm now going to create what I call a sort of learning model. So I say now I call my network, my neural network, I'm calling it new P, that's a single layer. Then I define my range. Let me just define my input range as this. S1 is this, and then Y1 is 170. And then my next one is 10, and then 80. Oops, what have I done? Okay, what is it? It's telling me this one is input new P. Okay, sorry. Then I have to just put one range. Okay, 1. Okay. Okay. So now view. Just look at what will happen. View net. Are we saying that Now, so this is the, when I did a view net, this is what I got. This is what I got when I did a view net. So you see that this is a graphical system that will give me my neural net, my network that I've done. It's telling me that I've provided two inputs. The input is S1 and S2 pair, but the number of samples are many. But each input, each sample, I provide an input and output. And then we can see that each input, it has the connection weight, and then there is a bias, and then they go through the summation process, and then from there, it goes through the transformation function. It gives, so this layer that you have, that is each neuron. This is what we are going to see. So now I'm only using just one neuron. If I'm going to use more neurons, I can do that and do more neurons. And then you can see the number of neurons. So let me do one that will give me more than one neuron. Then you can see something else. When we meet Friday, then we will take you through more of that demonstration. So now let me come back here and then do this. Let me change it to 3 neurons. And then I say now view my net. Now let me share with you what you are seeing here. This is what I'm seeing. So you see that when you do that, it is telling me that I have 3 neurons. So it has put the input are 2, S1 and S2 for each sample. But I have 3 neurons. Neuron 1, neuron 2, neuron 3. And now the output, I have 3 output neurons. So each neuron has an output. So this is where we see the graphical representation of how the system works. Now, based on this, I'm now going to, I can go on and on and on and on. So I can now do a plot of my function, and you can see what is going to happen. Like I said, where we meet on Friday, this is hands-on, so you can't see it well. When we meet on Friday, we'll go through, each of you will test these things. But that is not the actual development. We are going to use Python programming. But this is to give you a flavor of how, because when you come to the Python, you will not see images like this. You will not see this. So this is just to give you a sense of how that network looks like. Okay. Then then we have some of the data that we'll be using. We can share some of them with you. Now I can then do also a plot of this. Then you can now see what I'm going to do. So now having gotten this, let me now plot my data so that you can see how the data looks like. Okay, so I can now move to the next step now. Then I do, let me go back because I'm dealing with only one neuron so that it doesn't distort my information flow. So now I can now do the next step where I'm now going to plot my variables. I'm going to plot my P and then my T. Oops. The number of rows more than this. Do I have more rows? Let me count. This is 1, 2, 3, 4, 5, 6, 7. Up high. So we have, okay, so 1, 2, 3, 4, 5, 6, 7. 7. This is 7. 8, 9, 10, 11, 12. Okay, so I missed one more. So the t, let me now go back to plot one more. The t. So now add one more. Let me add 0. Okay, so I can now plot this one now. Okay, p must be 1, 2, 3, or 0. Oh, come on. Two, 3, 4. Okay. Okay, let me see something again. Let's see something. Okay, so let me do something, one more thing. One more. Let me see. Okay. Very good. So now let me now share my plot with you now. So this is the plot. The data that I shared with you, this is how the plot looks like. This is how so you see that I have the plus plus and then the 0 0. So one of them is denoting the 1 class, and the other one is denoting the 0 class. So this is the data distribution that I have. So when you come to, you see that if you look at the outline we gave to you, we have written something that we are going to do data distribution. So visualization. So we visualize this data set, and you can see a plot of how the data distribution looks like. So then we are now going to this is the first one. That is the X1, and the other one is X2. That's what it is. So now we are now going to my S is what I call my P. So we are now going to do the next step. And the next step is we are going to train this data. So I'm going to ask the network to train this data for me. So I'm now going to go back and then say train the data. I say train net 2 is equal to train my net, and I'm training it with the input variable and then the target variable. That's what I'm asking it to do for me. So it's, what is the problem? Okay, error using input samples. What is it? Net 2 is equal to train net. What is the problem here? Net 2 is equal to train net. I said train my network for me. My network is the one that I viewed. Okay, let me do again. Net. Okay. Input and targets have different number of samples. How? We've just done it right now. Oh, I didn't do the right word. Okay, please give me 1 minute. I have to check the number of samples again. Mouse is behaving, misbehaving. This is P. Where is my P? I have P to be equal to okay. Then T to be equal to, let me just T is equal to input and target have different numbers of samples. So there's one that is not correct. Okay, this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13. Hi. Okay. 13. Okay, so I have to delete one of this. Okay. Okay, so now I can now train the network. Very good. So now the network has trained now. This is a training. So it has trained now for me. So you see that now we have all these details. We'll be doing that under the Python programming. So don't worry. Friday, I will give you this. So you try your hands on this, some of them. So we have the input. This is the neural network. So we provided a number of samples, 10 or so 11 samples. Now we said the network should train. It has trained the network. Now the training is giving me a certain information here, which we will deal with all of them later on when we meet with you on that. Now it's like I can now see the training performance of the network, and I can also see the training state of the network. So I can plot every single one of them to see the various information as I go along. So when we come to the, what do we call it? Now the network training. Now, supposedly, if the network has trained enough, then I'm now going, if I believe it has trained enough, I can now do something else. I can now test the network. If it has trained, it means it has learned the relationship between the input and output pair for all the data set that I gave to it. So I can now test it with an input data, and I'll ask it to now give me a response as to whether the data that I provided is able to correctly classify it for me. So this is what I'm going to do as the next step. Then I close, and then we meet on Friday in the lab for continuation and actual demonstration. So for those of you who have MATLAB in your, the reason why I was going to use Python, but the reason why because we haven't introduced you to the Python training yet. So I'm only using this to demonstrate to you. So those of you who have MATLAB on your machine, when you come, we'll do a demo on that. And I'll also show you some other things relating to this so that you can play your hands on them until we come to the Python programming, where we'll now go through the details of each of them. So now that my model has trained, if it has trained enough for me, then I now move to the next step where I now want to test it with an input data. So I will say that, okay, I want you to test this for me. So I will create a test data. And my test data, I'll provide an input to it. And I said, okay, my input will be 1, 2, 1. And then I have my X1 is this, and X2 is 27. So I now do this. Now I am now going to now pass this. If my model has trained, then I'm now going to now pass my output into that. So I'm now going to pass this input to the model to see whether it should. And my model that I train is, I call it net2. So I will say that y is equal to net2, oh no, sorry, I'm not going to simulate. So I'm saying y is equal to net2. Okay, no, y is equal to net2. I can now pass in now the test data. It has classified for me. It says that my output is what? 1. So I have 2 classes, either class 0. So if you look at my training data set, I said you either a male or a female, where I say the male is 0 and the female is 1. So I have 1, 2, 3. All the students that I have 1, 2, 3, 4, 5, 6. 6 of them are males, and then 1, 2, 3, 4, 5, 6, 7. 7 of them are females. So now, based on the data that I provided to it, if my model has worked very well, then it tells me that this input sample that I provided, it classifies it as a female. So this is how pictorially, I mean, this is how the neural network development process looks like. So that given our training data set, so let's say, for example, for each data set, you see that this is a pair for one student. So S1 will have this. This is a second student. S2 will have this. And this will be X1 and then S2 input. So each student has two features or two attributes I'm using. So student 1 has this, student 2 has this, all the way to the number of students. So we can create any numbers, and then we can create any fictitious targets, and we can use that to be able to do our basic concept. I will end here. If anybody has any question, then you can ask. If not, then Friday, we will now do we'll continue and then do a demonstration more demonstration on that. But that is not the training yet. This is just introduction to let you see how things work out. So if anybody has any question, if anybody has any question, please. Any question?
Hello, doctor.
Yes, please.
Please, thank you so much for the presentation. Please, my question is, about the neural network. You said the inputs, after the inputs are being sent into the neuron, there will be a bias added. Please, I don't understand the bias, where it comes from.
Okay, so this is from what the biology people tell us. Then I can also talk about it from with the electronics, the computer engineer we deal with electronics and programming. So I can tell about that side. You see that they tell us that every neuron has to be activated or has to be energized. Let me put that, if that word is correct. Every neuron will have to be energized. So the energizing of the neuron, we have to provide some, if you call it, some excitation to the neuron so that it will be able to fire. So this is how it works out. Every neuron can excite, it has to give an output, but before it gives an output, it has to be excited before it can give an output. And that excitation is what we refer to as the bias. Now, when you come to electronics and you are dealing with a transistor, you see that the transistor, this is how the transistor looks like. This is the base. This is the collector. And this is the emitter. Now, we always provide what we call a voltage here. We call it a VCC. That is a voltage that we use to excite the transistor for it to work. In the same way, that is the same analogy we have here. So we bias it with a unit value. This is +1. But this connection here will have a value which we don't know. So all the connection weights, when we come to the next segment, we will explain to you. What we do is in the machine learning development, we always generate. Please, can you mute for us? We generate random data because we don't have to, over here, I just feed the values. But in actual application, we don't have this. We don't know if there are 1,000 of them. You can't write each of them the value. So we normally use a random generation process to generate random data. And then so this random data that will be, let's assume that this value here is minus 0.21. So the training process will help refine these values until it comes to an actual value that is supposed to be what is supposed to be. And that is what we say that it has learned. And this now tells us that when we say it has there's no memory, but the information is stored in the weight. The final learning process, the final value here will be what the knowledge is about. So as we go through the processes, then we can further bring it down to you to understand what those things mean. I don't know whether I've answered your question.
Yes, please. Yeah, it's fine now. Thank you so much.
Okay, right. So we will meet on Friday, and then we will continue to finish that segment of what we are doing now. And then we'll do a bit more of some demonstrations on this. And after that, next week, we will start with the second topic, which deals with now preparing how we can translate, given the problem, how do we know that we can use machine learning to do that? And then once we are done with that, the second session, then the third session will now start with the Python programming. Okay. So Ken, do you have any comment, any remark?
No, but then I just want to thank everyone who spent time to join us today. And also, if you have a friend who is supposed to be part of us and is not coming, just inform the person that we are in the process of replacing those who are not joining or those who are not attending with those who are waiting. There's a waiting list. So after Friday, there will be a total replacement because some people are on a waiting list and some people are in, but then I think they are almost at an exit list. We are not pushing anyone out, but then we want commitments. And if it is not going to work out for you yet, not because of the fact that you are lazy, but maybe you have other things competing for your time, no problem. Other years you may join, but for now we need people who are committed. I think that's all I have, Dr. Mills.
Okay, thank you very much for bringing this to my attention. So now, this is what I want us to do. We can generate the list, we have it in the database, so we can extract and make it in by department so that we can convert to a PDF and share on the platform. So that if we can do that between by tomorrow, or so that at least by the close of work tomorrow, so that when we share it on the platform, at least they will know. Because after Friday, because almost every time, some of the senior level students have been coming because they didn't, some of them registered, but because of the shortlisting, they couldn't go through. And some also didn't register, but they said they missed the announcement. So we've been getting news, and people have been coming. So please, we'll put it there by tomorrow evening. Latest, it will be there by midday or something. Latest by 5 p.m., it should be there.
Sure.
If you know any of your colleagues, we'll do it level by level. If you know colleagues that are on that list and they haven't shown up, you let them know that after Friday, because we are moved to the next level. So after Friday, we'll replace all of them and then we'll bring in new people. When we are done after this session, when we are done with this, I don't know, maybe there will be another one, but that one, I can't guarantee when. But certainly it will not this year, it will be next year. Okay, so thank you very much.
Thank you, sir.